On a warm spring day in 1707, Leonhard Euler was born in Switzerland in Basel, a city overlooking the Rhine River, to Paul Euler, a Calvinist pastor, and Margaret Brucker. He was the oldest out of 4 children. As a young boy, it was apparent that Euler's talents had a natural inclination towards mathematics. At just 13, he enrolled in the University of Basel, one of Switzerland's most prestigious higher ed institutions. Eventually, Euler graduated with a master's in philosophy. Euler's father wanted him to follow in his footsteps and become a pastor to preach the word of God. So he made him study a lot of stuff he didn't care for, like ancient Greek and Latin. Euler's tutor, Johann Bernoulli, a famous mathematician, decided to convince his father to let him study math, as he saw great potential in the kid. Then, it was decided that Euler would pursue math instead of preparing sacraments. Euler then returned to school and obtained a degree in mathematics. Shortly after, Euler entered a competition hosted by the Paris Academy where contestants needed to find the best arrangement of masts on a ship. Euler won second place, owing to Pierre Bourget, who was later crowned the father of navigation. Slightly saddened by his loss, Euler decided that he wanted to find work. He left the Basel Academy, traveled down the Rhine River, and arrived in St. Petersburg, Russia. At this time, the Russian Tsar Peter the Great was heavily inspired by the advancements of Western Europe under the Industrial Revolution. He decided to modernize Russia by implementing a series of industrial and educational reforms. As a result of these reforms, the St. Petersburg Academy of Sciences was built. Euler joined the Math and Physics department at the Academy as the department director in the year 1727. Shortly after, Euler left the academy that same year and enlisted in the Russian military as a medic. He served for 3 years. In 1730, Euler returned to St. Petersburg, and he was given a permanent position at the St. Petersburg Academy as a physics professor. Euler's days in the military thus ended, and thus began his long and fruitful academic career, during which he published many famous works, including Mechanica, in which Euler perfected techniques of mathematical analysis and applied them to problems involving mechanics. Shortly after the passing of the Russian Tsar Peter the Great, political turmoil was rampant in the country. Fearing trouble, Euler fled to Germany, Prussia, where he took a job at the Berlin Academy. Around this time, he published over 380 research works, including his most famous ones, Introduction to the Analysis of the Infinite, which was the foundational work for mathematical analysis, and Foundations for Differential Calculus, which eventually laid the groundwork for the discipline of differential calculus, which concerns itself with studying how rates between quantities change. When it came to Euler's love life, he married Katharina Gazelle, the daughter of a painter. They had 13 children together, but only 5 made it to adulthood. As Euler dedicated long periods of time to his work, his health began to deteriorate. He became nearly blind in his left eye and developed cataracts in the other. Euler, however, shrugged this off, saying in his own words, "Now, I will have fewer distractions." The year was 1760. The gunshots of the 7 Years' War can be heard across the European continent. Russian forces, advancing towards Prussia, burned down, sacked Euler's house. He barely escaped with his life. 1766, Catherine the Great ascends to the Russian throne. The political climate of Russia begins to settle down once again. To compensate Euler and to thank him for his previous contributions, he was invited back to St. Petersburg and given a high-paying position at the academy, and life was good. However, tragedy seemed to have acquired a taste for Euler. His house burned down shortly after, and his wife passed away in 1773, after 40 years of marriage. One day, as Euler was discussing the discovery of the planet Uranus with his family, he suddenly collapsed to the ground. The year was 1783, and the famous mathematician succumbed to a brain hemorrhage in St. Petersburg. After an eventful and accomplished life, Euler was finally laid to rest at the St. Alexander Nevsky Monastery in St. Petersburg. In his life, Euler was a prolific mathematician who came up with many theorems and novel mathematical ideas, one of which involves the Königsberg Bridge problem. The Königsberg Bridge problem had perplexed mathematicians for decades. It involved a topological map of the city of Königsberg, Prussia, now Kaliningrad, Russia, in which the four landmasses of the city were connected to each other via 7 bridges, arranged in the fashion depicted above. In short, the problem was to find a path through the city that involved crossing each individual bridge just once. However, no matter how people tried, they would always end up either crossing the same bridge more than once. Some got creative and decided that the problem could be solved by deleting or reconstructing additional bridges, but those moves were all illegal and people were still confused. This was until Euler proved that the problem, in fact, had no solution at all. Euler realized that since the goal is to cross each bridge just once, that traveling within each landmass was irrelevant. All that mattered was the sequence of the bridges that were crossed. Euler then decided to take an abstract approach to the problem. He denoted each landmass as a vertex or node, and each bridge was an abstract connection or line, which is a unit that connects at least 2 vertices as a plane. By doing this, Euler created something called a graph, and no, not the linear, exponential, x and y axis polar stuff. A graph, in this context, refers to sets of nodes or vertices along with lines, or as we call them, abstract connections, that connect the vertices. The discipline which focuses on the study of these graphs is called graph theory. Euler proved that since the landmasses are joined by an odd number of bridges, it would be impossible to travel each bridge just once. By proving that the Königsberg problem cannot work, Euler in turn proved the first theorem in graph theory, and paved the foundations for the entire discipline. Centuries later, the study of graph theory, which had its origins in a leisure problem, has expanded beyond the scope of just mathematics, with numerous applications in fields such as computer science, social science, and operations research. Even if your career has little to nothing to do with STEM, graph theory enters your life even when you use social media. Say, Joe has a Facebook account and is friends with Nathan, Philip, Eric, and Ryan. Then we can each represent each individual using a node, and their friendship status as an abstract connection. Now say Nathan is friends with Philip, Eric is friends with Ryan, and Ryan is friends with Nathan. Then we will draw lines connecting the nodes as shown here. It's kind of baffling to think that whenever we're accepting a friend request, or blocking or removing someone, you're utilizing concepts that originated over 250 years ago. So, the next time you add more friends on social media, or delete a few for a free Whopper, you can thank Euler and his brilliant mind. Another famous theorem Euler discovered and pioneered was his characteristic for polyhedra. This was called Euler's characteristic, in which Euler discovered that for any given polyhedra, defined as a 3-dimensional entity with polygonal-shaped sides, straight edges, and vertices, you may take the number of edges of the object, subtract it from the number of vertices, and add the number of faces, and the resulting value is always 2. This number is what's referred to as Euler's characteristic. No, try it. Take this octahedron, for example, which has 6 vertices, 12 edges, and 8 faces. Using Euler's characteristic, we take the number of vertices, 6, subtract it from the number of edges, 12, and add the number of faces, 8, to obtain the value of 2. Similarly, taking the cube, we repeat this process and obtain the value of 2 once again. As far as applications go, Euler's characteristic is involved with the construction of soccer balls by sports equipment manufacturers, as the process involves the connection of multiple hexagonal and pentagonal surfaces being conjoined together to form the ball. To explore this in depth, we denote each pentagon as X and each hexagon as Y. To find the number of faces of the soccer ball, we simply add the number of 2D shapes there are. To find the number of vertices, We know that there are 5 vertices in a pentagon and 6 in a hexagon. Divide that by 3 as 3 pieces meet at each vertex, and for the number of edges, repeat this process but divide by 2, as 2 pieces are joined by every edge. Then, by using Euler's formula, we obtain x over 6 as the characteristic. And as per the theorem, the characteristic is always 2, so therefore x equals 12. In other words, each soccer ball has 12 pentagons in the stitching. Euler's discoveries spanned such a large scale that the mathematical community got tired of naming all these things after Euler. Therefore, they decided to name a bunch of things discovered or proven by Euler after the second person who discovered or pioneered them.